I don't know why do we use Ackermann's, although we have such of a easy method, even though we have such of an easy method to solve for k. Alright, but never mind, let's just do it. Alright, to use Ackermann's method now to actually solve for these things. Alright, for Ackermann's, you need to first transform your transfer function into a state space system first. Alright, this is what we have done in the first video of our series. Alright, we changed to a state space, and then now we'll continue by determining our closed loop polynomial. This s squared plus 30s plus 200 comes from where? It comes from your desired closed loop poles, right? Minus 10 and minus 20. Alright, your roots is minus 10 and minus 20, and therefore I have s plus 10 and s plus 20. And you may wonder why here minus 10, this one is 10. The roots is minus 10 means what? Is if s is minus 10, then 10 plus 10 is equals to 0. Alright, so the roots is just that the s, whatever s value that makes everything equals to 0 is the roots. So if the roots is minus 10, then minus 10 plus 10 is equals to 0. So it's the roots, if happen that you forget. Anyway, therefore we take our desired closed loop system, we multiply it and expand. When you expand it, you will receive x squared plus 30s plus 200 as a form. Alright, so you will have this form which is your desired poles, your desired closed loop. I repeat again, it's closed loop. Okay, your initial one, which is the open loop one, is s squared plus 7s plus 12, right? So you want to shift your s squared plus 7s plus 12 into s squared plus 30s plus 200. Alright, so this is the same thing as the last video, but I just continue now. So our purpose now, and we have chosen our closed loop poles already. We have set already. We are off to go. So once you choose your closed loop system, alright, instead of s, you write it as a square. Okay, so your s square will change to a square, your s will change to a. Alright, while your 200 will just write as an identity matrix. Alright, I should write down the step by step. The first step, alright, is to write your state space, which is all over here. Yeah, your state space. The second step is to determine your closed loop poles. You want to know which closed loop desired poles that you want. So this is your desired closed loop poles, the one that you want. Okay. The third one is to change your s square to a square, your s to a, and your 200, your s to the power 0 to I, your identity matrix. Now you can simply, a square is what? Alright, your a square is, this is your ax plus bu. So your a is this matrix. If you were to a square it, we will have a times a. Alright, so just go through with you with the matrix multiplication is that minus 7 times minus 7, you'll have 49. Alright, and then minus 12 times 1, you have minus 12 over here. And then minus 7 times minus 12, you have 84. Alright, minus 12 times 0, you have simply plus 0. Okay, then 1 times minus 7, you have minus 7. Then, minus 7. And then 0 times 1 is simply plus 0, so it's just simply minus 7 also. And then 1 times minus 12, you will have minus 12. 0 times 0 is simply 0. So what you have is this matrix. Alright, I just want to convey to you is that this row times column, and then row times column again, and then this row times column, this row times column again. You get what I mean? So I just want to convey to you that the matrix is, this multiplication is this. And if you were to do it, alright, the answer for your a square is this one. You can just try in your paper. Alright, I'll not go through with you in other stuff for this matrix anymore because I'll go through to you now. Alright, so therefore this matrix multiplication for your a square is this one. Alright, well 30a you just simply multiply with your matrix A lah. So it's 30 times your A. You will have a number minus 210, because minus 7 times 30 is minus 110, then minus 12 times 30 is minus 360. You get what I mean? And then Yeah, I think you get what I mean already. Alright, then you just elaborate lah. Eventually you'll get this one. Okay, your identity matrix is simply 200, 200, 0, 0, because the rest are 2 times 2 matrix. Alright, these are all 2 times 2 matrix. Remember that. Alright, if you have a 2 times 2 matrix of A. Alright, because your A, your state space system over here is a 2 times 2 system. Okay, so the rest should be 2 times 2. Just take note. Okay, so the fourth step now is that you need to determine your RC, your controller rank, your rank of a controller, if you still remember. This is the part that comes in that applies what we have learned earlier, right? It's the test for controllability and observability is the test, if you still remember the test. So we use the test somewhat, but however, this is definitely a fully controllable system. Alright, it's because this column is always independent from this column, because you cannot represent this column with this column. You remember? Alright, so you cannot represent this column with this column, so to speak, if you cannot see my arrows. So yeah, so the rank of the controllability matrix, alright, is B, AB. This is for 2 times 2 matrix. You have B and AB. So you have a matrix B, which is your this thing over here, your B, and then your AB. So you're gonna take your matrix A and gonna multiply with your matrix B, or your vector B for this case. Alright, this is for 2 times 2. If it's 3 times 3, then you will have A square B. If it's 4 times 4, A cube B, so on and so forth. Alright, so I hope that this is pretty clear for you. So in our case, we have only 2 times 2 matrix, so we only have a 1 row, 2 columns. Alright, so for this case, this B is 1, 0, which is our 1, 0 over here. Alright, this is our BU, right? Our B is 1, 0. Okay, if you were to take A, the A matrix multiplied by your B, what you have is your -7, 1 over here. Okay, so this is the fourth step. You're going to determine your rank controllability. The fifth step is to inverse. Alright, inverse is simply just to recap, because with this example it's very tough to prove to you the inverse. By using this example A, B, C, D, I can prove to you. So if you imagine if your RC, alright, is equals to A, B, C, D lah, some matrix. If you were to inverse your RC, you're going to take 1 over your determinant of your RC, meaning AD minus your BC. Alright, AD minus your BC, if you still remember. Alright, multiply by your matrix. So this A and this D will switch place, D and A, and then this minus B and minus this C and B will becomes minus C and minus B. Okay, and therefore this explains why your -7 over here becomes +7, because you have switched the negative sign. Alright, and then the reason why I say that I cannot represent the inverse well is because this is 1, this is 1. So you cannot see that AD has switched to DA, because they are all 1s, the same number. Alright, as for your determinant AD is actually A times D. For our case is 1 times 1, so therefore is 1, minus away B times C. So B times C is -7 times 0, which is 0 lah. So 1 over 1 times D minus B minus CA, which this whole thing is just this one. Okay, I hope that this is pretty clear for your inverse case. So be very mindful of this thing. Alright, and the last one is to form your K. Alright, your K is just simply if it's a 2 times 2 matrix, alright, you'll have 0, 1 at this point. Alright, if you have a 3 times 3, you have 0, 0, 1. If you have 4 times 4, you have 0, 0, 0, 1. If you have more than that, you have 0, 0, 0, 0, 0, all the way to whatever thing the last one is 1. So take note that the last one is always 1, the rest are all zeros. Alright, this is the first form. Alright, I can call this A. And then this RC inverse is B, which is what we have shown you earlier. And then this is our ACL, our closed loop matrix, if you remember. Your not ACL but rather we call this the alpha. Alright, this thing over here is your this thing that we have solved. Okay, so this thing comes from the understanding that if you have 2 times 2, the last one is 1, the rest of it are 0. Alright, this is just simply something new to you, that's just to take note of it. Alright, while RC inverse we have found, alright, while the alpha A, alright, this thing we have found also using your ACL system. You have this thing. So if you were to multiply with this matrix multiplication, you'll get 23188. Okay, so it's your K. Therefore, just take about 5 seconds just to take note of the steps. The first step is to do this, the second step is to do this, third step is to do this, things like that. Alright, just take a few seconds and look at it. Alright, so I think you have looked at it. So the first step is this, second step, first step, do state space, second step, do out the ACL, the third step is to change the ACL to a alpha CA system, which is a matrix. The fourth one is to change your controllability rank, to find your controllability rank, and then fifth step is to inverse it. Sixth is to form out all this thing and eventually find your K. That's all. Alright, so this is the Ackermann's method. Alright, not to forget, alright, this is your K2, this is your K1. Alright, and then this is your A2, this is your A1. If you were to form into the closed loop system, alright, for a canonical form, what you have is this form, right? If you still remember, I'll just simply write now because this is quite messy. So I'll only take this first 2 by 2 matrix because we are only doing with 2 times 2. So I'm taking this thing and simply rewrite form over here, alright, and then alright, just simply sign in the values already. Alright, the value for A2 is what? A2 is simply 7, alright, because the canonical form for the open loop is minus A2. So A2 is 7, so it's minus 7. So therefore A2 is 7. Alright, if you don't know what I mean, alright, I'll just simply paste the, if you remember, we start off with a transfer function. Alright, this transfer function is over here. This is our open loop transfer function. And when we close loop, we want our poles to actually shift to this ACL, right? To this thing over here. S squared plus 30s plus 200. Alright, so in order to write in terms of a state space canonical form, alright, this thing over here, I say that this is A2 and then this is A1. Okay, and then we rewrite, because the general form of a canonical is minus A2 minus A1 1 0 for a 2 times 2 system. Okay, where this is A lah. A matrix is equals to this. So I just simply sub in, because A2 is 7, so I just start as minus 7 and minus 12. Okay, which is over here lah. So therefore now I will need to rewrite things in terms of A1 and A2 also, right? So therefore my A1, my A2 over here is 7. Alright, my K2 over here we have proved to you is 23. So therefore plus 23. Alright, so this whole thing is minus, so 7 plus 23 is 30, so we have minus 30. Okay, so therefore I can simply write as minus 30 over here. And then A1, what is A1? A1 is 12, right? Because A1 is 12, the canonical form for the open loop is minus A1, so A1 is simply 12, so minus A1 is minus 12. Alright, so I think you get what I mean. So A1 is 12 in our case, plus K1, which is 188. So I have 188. So therefore 188 plus 12 is minus 200. So I have minus 200. And then the rest is simply the same, 1 0. So this is my A minus BK closed loop matrix times X. Okay? And then if you were to apply your closed loop, you can go to l7v3 and watch this video, alright, for the closed loop system. I actually take it from there. And from there we have proved to you that your closed loop transfer function can be written from this stuff. So just sub in your C matrix, alright, your C matrix is 0, 2, and then your x0 is your initial value or initial state, your SI is simply some stuff, and then minus A minus BK, which is the one that we have found, which is this one, right? Ours is A minus BK. Alright, what we're doing now is to find the A minus BK, and then, which is the closed loop, and then you inverse matrix. Eventually, when you sub in everything, you will eventually represent your transfer function. And this is where you can acquire your closed loop transfer function based on all the steps. Alright, in order to shift your poles from whatever pose that you want to the pose that you want. Shift your initial pose to whatever pose that you want, which is your s squared plus 30s. Previously was s squared plus 7s plus 13 if you, or 18, or sorry 12 if you remember. So this is the initial one, and then we shift it down to the closed loop pose over here. Okay, so therefore this is the case. Yeah. So this is the Ackermann's full method of applying whatever thing to find your k eventually to eventually find your closed loop transfer function in a very general method. Alright, so see you in the next video for other stuff.